Hi there, and welcome to my YouTube channel. In this video, I'll be explaining the theorems of circle geometry using very simple terms. But I believe before we dive into this, you can still remember the properties of a circle, like its radius, the chord, sector, segment, and so on. So the first part of this theorem involves triangles. Two radii forms an isosceles triangle. So when you find two radii, you can join a third line to find an isosceles triangle, to form an isosceles triangle. Then the next one involves a bisector, a perpendicular bisector of a chord. So the perpendicular bisector of a chord would always pass through the center of the circle. So this perpendicular bisector or perpendicular, it cuts the chords, it divides this chord into two equal halves. And guess what? You can actually complete this. Join a line from the end of one chord to the center, join another line, and guess what? The theorem applied here can still be applied here. Two radii forms what? An isosceles triangle. The third one involves a triangle in which all the vertices or the corners lies on the circle. And it's not just any of the vertices. These vertices, two of these vertices must pass through the center of the circle, forming a diameter. So just guess what? Anytime you see a circle and then you have in it an inscribed triangle, check if one of the lengths of the triangles forms the diameter of the circle. If it is, then you can apply this theorem. The theorem says that the angle in a semicircle is equal to 90. So, of course, the diameter divides the circle into two equal parts. So you have a semicircle, so the angle in this semicircle is equal to 90 degrees. The next theorem is angles in the same segment are equal. But guess what? When you see this theorem, all you just need to look out for two triangles in which the vertices or the corners lies on the circle. And if these two triangles share a common base, then the angle facing this common base must be equal. I'll try to include another one here. And this is also equal like the others. The next theorem is the one that we call the alternate segment theorem. It's just a triangle connecting with a tangent. So the angle that is formed between this chord and the tangent is always equal to the angle in the opposite segment. So this is a segment. It divides it into two segments. The angle formed here is equal to the angle in the opposite segment. It's quite easy. So let's try something. What if I try to draw something like this? So if this is A, it means that this is the angle in the alternate segment. Okay, we move on to angles, quadrilaterals, cyclic quadrilaterals. So a cyclic quadrilateral has the vertices or the corners on the circles. If you have a circle like this, and then you have a quadrilateral that looks like this, it is not a cyclic quadrilateral. So this rule will not apply to this kind of formation. But if you have a cyclic quadrilateral, then this rule will apply. What is the rule? It says that opposite angles are supplementary. That means they add up to 180. Opposite angles in a cyclic quadrilateral add up to 180. Now the next theorem would be, or the next set of theorem would be involving cyclic quadrilateral, but then an exterior angle. So the angle that is formed when one of the lines of this cyclic quadrilateral is produced is the exterior angle. This angle is always equal to the interior opposite angle. The theorem here talks about two tangents from the same point. This is a common point from which these tangents are drawn. they always have equal length. They always have equal length. And remember the theorem that says that a line that joins the radius and a tangent forms 90 degrees. Yes. So that forms what? A new kind of gives us a new information. And of course, this is a quadrilateral A, B, C, and D. So the properties of a quadrilateral still applies here. I hope you find this videos very useful. Thank you for watching and look out for more videos involving examples with this theorem. Bye.